Hey everyone, and welcome back to our Python data analytics series. In this video, we're going to go over some simple predictive analysis using simple linear regressions and multiple linear regressions, as well as plotting these predictions and checking their accuracy. In our last video, we left off by looking at the correlation between research and total score. To further explore the idea of correlation, we should build a predictive model that is able to predict some value based on another value, to truly test whether our data is correlated or not. One of the most common ways to do this is by making what's called a linear regression. Before we get into the coding, I want to quickly go over what a linear regression is and how we're going to actually use it. So, as we know, any straight line in two-dimensional space can be graphed by this equation, y equals mx plus b. And basically in this equation, y is the y-coordinate, x is the x-coordinate, m is the slope of the line, and then b is the y-intercept of the line. So let's look at an example real quick just so we can go through this. So in this graph here, we have a line that is equal to y equals 5x plus 2, and it looks like this on the graph. The idea is, for any value of x that we plug in, we would get a corresponding y value. So if we plugged in, let's say 2 for instance, into this equation, let's say we plug in x equals 2 to this, we have 5 times 2 is 10, plus 2 is 12, so y should be equal to 12 when x is equal to 2. And we can actually see that if we go and look at our graph here. If we look at this coordinate right up here, it looks like right where x is equal to 2, y is equal to 12. So basically, in this y equals 5x plus 2 equation, x and y represent any possible x or y coordinates, 5 is our slope, and 2 is our y-intercept, and you can see the intercept here, right at 2, because that is where the x-coordinate is equal to 0, and where it crosses the y-axis. So, using what we now know about lines, let's make a definition for a linear regression. So, a linear regression is basically just a technique for predictive analysis, and it uses what we know about lines on a graph to estimate future values given old values. So the idea is basically that if we have a scatter plot that has tons of different dots that represents a wide array of data points, kind of like this one with total score versus research, we should be able to find a line that fits and approximate all these data points and minimizes the variance from the points, meaning most data points will fall around this line. If you notice here, if you look at the scatter points here, you can see that it definitely does follow an upward diagonal trend. So the idea of a linear regression is basically finding the line that actually matches this trend the best. And the idea is that if I were to make this line start near the bottom and then go all the way to infinity, a good model would have points still following the trend of this line. So this is all that a linear regression actually is. Basically a technique to find a line that best fits the data. If the model is good and the line approximates the data really well, we can conclude that 2 or more variables may be heavily correlated and can even use it to predict future values. So then how would a linear regression work mathematically then? So basically all we need to do to find a linear regression is to find the slope that we need, or our m value, and then find the y-intercept that we need, or our b value. Luckily in Python, we don't need to actually do any of these calculations by hand, as Python will do it completely for us, although we do need to know the commands to execute it. An equation like this that's just using y equals mx plus b on a dataset would be called a simple linear regression because we're just looking at two variables, x and y, where y is our dependent variable and x is our independent variable. However, we could add more x variables and coefficients to this equation, and it would mean that we're feeding in multiple different variables to predict a single variable. And this is what's called a multiple linear regression if we were to do multiple variables in that fashion. So if we wanted to actually look at this in the context of the data set that we're using, how would we select our variables and how would we figure out our simple linear regression line? Well, right here we're looking at the correlation between total score and research. So if we wanted a simple linear regression for this graph, we could have research as our x variable or independent variable, and then have total score as our y variable or dependent variable. In doing this, we would see the correlation between research and total score and model if research does truly affect total score that much. If we wanted to do a multiple linear regression, we could have research, talent, and commercial, for instance, all as our x variables, so having multiple variables, and maintain total score as just our y variable. So let's actually move on to our code now so we can try this out, and you can see what I mean. Okay, so the library we're going to be using for this is called sklearn, and it's one of the most common libraries you may see for data science or machine learning, and especially predictive modeling. So to import, let's just go in this code block down here, and I'm just going to write from sklearn import. I'm going to import two modules basically, and import model selection, and then also linear model, just as we would import any other library module. Another library we want to import, which happens to be one of the most popular in Python, is NumPy, and I'll explain why in just a moment. So for instance, just now, I'll just write imports NumPy as np like that, and then I'll just go ahead and run it just so we have it. Okay, so let's start with our simple linear regressions now. We found up here with our correlation graph that the best single variable to try and isolate and correlate with total score would likely be research. So let's actually go and declare variables for our simple linear regression. So I just want to set x equal to our research column. So I'm going to say x equals datasets research, and then I'm going to say y equals datasets total score like this. However, there's one modification we need to make to this before we go on. So by default, when we select a column like this, Pandas stores it as a one-dimensional data frame. However, the sklearn library we're going to be using doesn't accept this format, so this is where NumPy actually comes in. So to use the sklearn library, we'll want to turn this data frame into a NumPy array instead. So to do this around both these variables here, I just want to wrap it in np.array because np is our NumPy object. So I'm going to say np.array, wrap this whole thing in that, and I'll do the same exact thing for our y variable as well. And one final thing before we can go on. By default, lists or arrays are a singular row of data. However, in our model, we want to look at one singular column, not a row, so we need to change the shape of the array to be vertical rather than horizontal. And luckily, NumPy has a thing for this. So to do this, we can use NumPy's reshape function to the end of these lines here. So inside, we specify the shape that we actually want. So what I'm going to do is I'm going to type reshape like this, and I'm just going to put -1 and 1. So basically what this argument means is when we're using reshape, the first argument is in reference to the rows, and the second argument is in reference to the columns. If you put a number here that's like 1, 2, 3, 4, 5, whatever, that specifies the number of either rows or columns that you want. And if you put -1 in here, it'll actually fit the other one just to match whatever the other shape is. So basically what I'm doing here is I'm specifying we want one column, and then we're just going to fit the rows to match whatever our columns need. So I'll go ahead and do the same thing for our y variable too. I'll just type reshape -1 and 1 like that. Now that I've correctly shaped these variables as NumPy arrays, we can move forward with our simple linear regression. One very important aspect of linear regression and just predictive models in general is that we should always have a training set and a testing set. The training set will be used to actually train our model, and then the testing set will be used to test the accuracy of our model and see if it gets things right or not. If we didn't split it up and we used the exact same data for our training and testing set, our model would get 100% accuracy because we're feeding it the exact same data, which wouldn't make a whole lot of sense. So in this next line, I'm actually going to make our training and testing sets, and it's going to be kind of a long string of words, and it may look really confusing at first, but I'll break it down step by step. So I'm just going to go ahead and write xtrain, xtest, ytrain, ytest, and then I'm going to set it equal to model selection that we imported from our sklearn library. And then from that, I'm going to call the train test split method. And then I'm going to pass in 3 arguments, our x column, our y column. I'm going to set an argument of test size equal to 0.2. So what does this line mean? Let's first look at the right side of this equation and see what's actually going on. So it looks like a lot of words, but all we're really doing here is calling this train test split method from sklearn. So basically sklearn is the library, and from that we imported this model selection module, and then within that module we have this train test split method. Hence why we're calling model selection dot train test split, since we're accessing that method. Then we feed this method 3 arguments that we actually care about. The first argument, x, is just our x column that we made up here, so our research column. The second argument, y, is just this column up here, so our total score column. And then just as I mentioned before that we need to split up the training test and the testing sets, we need to specify how big we want each set to be. So the training set will typically be much larger than the testing set, so we're going to set our testing set equal to be 20% of our data set by writing test size equals 0.2, meaning the remaining 80% of our data set will be the training set. The nice thing about using this function is that it randomizes which values get moved into the training versus testing set, so we can run it multiple times if we want to gauge its accuracy over a multitude of runs. So what does this function actually do when you give it all 3 arguments? Well, what it does is it returns to us 4 values. It will give us all the x training values, all the x testing values, all the y training values, and all the y testing values. And it does so specifically in that order. So what we're doing is doing a multivariable assignment here, making 4 new variables that represent these return values, separating them by commas, and then assigning them to the results of this function. So now that we have this line, we've made our training and testing sets, we actually have everything we need to go ahead and make our linear regression now. To do that, all it takes is actually just one line. Let's make a new variable. Let's just call it linear. And we're going to set it equal to linear model, which is the module we imported from sklearn. And then we're going to call a linear regression function like this, just like that. So this line simply grabs a linear regression method from sklearn, so we're making a new model and assigning it to our linear variable. And then to actually train our model, it's just as simple as writing one line. So down here, I just want to type linear.fit, and then all we need to pass in is our x training values, and then also our y training values. We want to pass in the training values when we're fitting it because, as evident by the name, these are the values we're training the model with. Once this chunk of code is run, like this, go ahead and run it. We've now actually fully created our linear regression in just a couple of lines of code and now are ready to go and look at what our linear regression actually looks like and what its score is. So how do we go from here? Because it looks like right here, it didn't actually print anything off, so how do we know anything about our model? Let's print off some things from it now that it is trained. We mentioned earlier that the whole point of looking at linear regressions was to find the y-intercept value and the slope that made the line the best possible fit. So now that we've trained our model, we can access those values. So here's how we get the coefficient or the slope, and then also the y-intercepts. I'm going to go down in here, this line. I'm going to write print, let's just say, let's get the coefficient or the slope first. All we need to do is coef, and then with an underscore, and then to get the y-intercept, all we need to do is type print linear.intercept, also with an underscore. And make sure to remember the underscore at the very end, because if you don't have it, it'll give you an error because it won't recognize it. And then just so we can format this actually a little bit nicer, I'm going to add like a string here. I'm just going to say, let's say slope slash coefficient in this one, and then do a little, that should work here like that, do a comma like that. And then I will have another string here that says y-intercept like this, and just do it like that. And then if we were to actually run this code chunk now, you'll see that our slope or coefficient is equal to 0.813895, and then our y-intercept is equal to about 10.54. So what this means basically is that if we actually had our equation, that our linear regression equation would be equal to y equals 0.813895x plus 10.54456, like that. And this would actually be our linear regression equation that we found using this model. So this is cool to know, but how do we actually know how good our model is? Let's check it out. So to find the accuracy of the model, we need to pass in our testing sets of data to the score function. So let's actually go down here. Let's go ahead and just say print. We're going to do score, and then a comma here. And then to access the score, all we need to do is type linear.score, and then we want to pass in our testing value. So I'll say x test and then y test. And then if I run this, oops, remove that call in there. Okay, run this again. Okay, and you see that our score that we've gotten for our model is approximately 0.83. So one issue that we may run into with our data set is that since it's so small, if we're trying to score our data set, using a simple linear regression is going to have some drastically varying results. So if I keep printing this off, it's going to keep printing the exact same number. However, I could actually retrain the model and then run this score again. We could get a whole new score. So to show you that, if I go up here, I can rerun the code here. Let's just reprint off our intercepts and slope because it'll change a bit. Run it again, and this time we got 0.67, which is much lower than the 0.83 number we had. And for this score, the higher number, the better. So a score of 1.0 would be like a perfect score, and then a score like a 0 would be like an awful score. That's like absolute lowest you can get. So the 0.83 was a lot better than 0.67, but I could literally just keep running this over and over, and then getting different scores because it is selecting, when you do this train test split here, like I said, it randomizes it, so it's going to be different each time for the score. But I could literally just keep running this over and over again. That time it's really low, like 47%. Let's just run it and see until we can get like a better score. So this time we get like a 92%. So let's go ahead and just stay at there for a moment. So the score isn't exactly a percentage, but you can kind of think of it like that. Obviously the higher number being better. And then what the score is kind of pretty much saying is that given your model, like for our model specifically, if we took a research variable, we could, with about 93% certainty, predict the total score variable. Generally, you want to shoot for a score of at least 0.5 because that's a score that's at least decent and showing some degree of correlation. Anything above like 0.75 is considered probably a good model, and then everything above like 0.9 is considered great or like a very good model. And remember, all these scores are in reference to the correlation between two variables. So certain independent variables will have lower or higher scores than others. But as seen by our previous correlation episode, the research column is probably going to yield our highest score, hence why we used it in this model. If we were to modify our x variable and make it something like talent instead, the score would change. So let's take a look at our actual scores versus our predicted scores. So to do that, let's go down here, and we can actually just use sklearn's predict function. So we'll just make a new variable, let's just call it predictions. And we're going to set it equal to linear.predict, and then here we just want to pass in our x testing values. So then let's loop through all the predictions and print off both the prediction and the actual value for each entry. So to do that, what we're going to do is write a loop here. We're going to say for x in range, and we're going to do it in length of predictions, so we run through every single prediction we've made. And then we'll just do obviously an indentation here. And then what we want to say is, let's just print off the predicted values versus the actual value. So I'm going to say predicted value like this, and then comma, we'll say predictions X here. We'll do a loop, and then we'll say actual value, and then comma, and then the Y test here will be our actual value. So basically all we're doing here is looping through every single prediction, and at each prediction we're printing off what the predicted value was versus what the actual value was. So now let's actually run this code and see what happens. Okay, so you see it prints off a whole list here of each of our X test values and their corresponding values. So if we look at these, we can see that pretty much all of our predicted values are somewhat in the ballpark of the corresponding actual values. So for instance, if we look at the first predicted value, we predicted this would be a value of 30.51 for total score. The actual value was 34.42 for total score. Let's go down a little more. We can see, like right here, we predicted a total score of 13.18, but the actual one was 11.79. And then let's look at this like one more. Let's say this bottom one here. We predicted a total score value of 30.30, and then the actual value was 31.36. So generally you can see that all these values, all the predicted values I should say, are all relatively close to the actual values that we're seeing. And this is actually the sign of a decent or good model. If we were to have a lot of values that were wildly off, because keep in mind like this would be out of a scale of 100 because total score is 0 to 100. So if we had like a predicted value of like 30 and then our actual value was like 80, then that would be really bad because we're like way off on the prediction. But as you can see from all these, we're actually decently or relatively close on almost all of these. So something that would be super helpful would be the ability to just plot these correlation scatter plots with our new linear regression line added to it to help us visualize how effective our model actually is. So let's go down here to our actual new code block, and I want to make a scatter plot that just takes in the training values of X and Y. So let's say plt.scatter. We're going to pass in the training values of X and Y, so basically the bulk of our data set. And then what we want to do is plot a line that shows our linear regression model. So it'll basically be corresponding to the predictions that we made. So let's do on top of this scatter plot, we'll do another line. We'll say plot. Then we're going to pass in our X testing variables as well as the predictions we have made. And then at the very bottom, like usual, we're just going to type plt.show like this. And then now if we actually run this, you'll see that we get our original research and total score correlation graph, except this time it now has our linear regression line added to it. Let's go ahead and just add some labels real quick. I'm going to add plt.xlabel. I'll just call that research. And then these will obviously be just to help us look at the graph a little neater. Say total score. And then I'll write plt.title. And we'll do total score versus research with linear regression like this. And then when we run it, same exact thing, except now we just have labels on our graph. So what is this graph actually telling us? Well, each of these individual little points or the dots you see from our scatter plot are coming from our training set and represents the vast majority of our data points and where they fall. And then this line represents the linear regression model using our X testing values and our predictions to try and fit a linear function to all the data points, which is in the form of a line. One thing you may notice is that because the predictions don't go on for infinity, the line simply stops at its last point. If we, however, wanted to continue this line to infinity and then all the way down to its intercept point, we could just add one line of code to this. So there's a function in the material plotting library that is called axLine that helps us continue a line infinitely. All we need to do is give it the slope and the intercept, and lucky for us, we've already found those things. So to do that, let's call our plt.axline function and just pass in our intercept and our slope. I'm going to type plt.axline, and then what it wants for the slope is an argument called xy1. So I'll say xy1 equals, and then we want to pass in a coordinate which represents our y-intercept. So our y-intercept is always going to be where x equals 0, and then whatever our actual intercept value is. But we want to make sure we convert it to a float. So let's do float linear dot intercept like this. So this will be the coordinate of our y-intercept. And then what we want to do is then pass in the slope of the graph. So we're going to say slope equals, and then we're going to pass this in as a float as well. And then we're going to say linear dot cof to get our coefficient or our slope. So again, all we're doing here is passing in two arguments. We're passing in the intercept and the slope. The intercept is just this xy1 argument here, and we're just setting it equal to a set of points that has 0 for the x coordinate and our intercept for the y coordinate, as all y-intercepts always have an x value of 0. Then we just pass in the slope as our second argument here, which is just the coefficient of our model. We wrap both of these numbers in a float method because we're converting them to floats, otherwise it'll give us a warning. So now if we actually run this graph, you'll see that we now have a regression line that goes all the way from our y-intercept all the way up to infinity. And that's pretty much it for simple linear regressions. We learned how to convert the pandas data frames into NumPy arrays, use those to generate our training and testing sets, and then use those to fit our model and then look at all sorts of scores and this visual aid to help us see the accuracy of our model. So one last thing I actually want to do is look at the idea of multiple linear regressions. And it's actually almost the exact same steps, except in multilinear regressions, we just select multiple x variables instead of just one. Because it follows pretty much all the exact same steps, I'm just going to modify the code we've already typed instead of typing up a bunch of new code. I'm going to go ahead and just go back up here to this chunk where we're actually making our model. So to do that, let's go back up to our x variable here, and let's actually select multiple columns instead of just one. So I'm going to remove this reshape thing. Instead of having to do like a single selection, let's do a multiple selection thing. Let's use a lock function to get let's get every single row and then all the columns or all the variables from, we'll say, talent all the way to commercial. And then we're doing this so we can look at every single numerical column besides total score and see how all these factors in combination are able to predict the total score. Because if we go up here to our data set, scrolling, you'll see that, yes, all the numerical columns, it's everything from talent to commercial, and we want to use that to predict our total score. Hence why down here, we are selecting every column from talent all the way to commercial. And we don't need to worry about actually using this reshape function if we're selecting multiple things, because it's already more than one dimension. And so from that point on, everything else is the exact same, and we actually already have our multiple linear regression model. So let's run this chunk of code to actually fit our model, and then let's print out the coefficient and the intercepts. And now it looks like our coefficients are these numbers here, and our y-intercept is this number here. So what this actually does is whenever we have multiple variables, we're actually going to get a coefficient for each variable. So we should have 7 variables total, I believe, because we have 7 columns. So for instance, the coefficient for like talent, for instance, would be this number. And I believe our second column is, second column should be infrastructure. So it would just go in order. So this is our infrastructure number, and then like our research number, I believe, or operating environment, whatever the order is of the column. So basically, yeah, each variable has its own corresponding coefficient, and then we have one y-intercept as usual. So next, let's take a look at how good our score actually was. Let's print it off here, and wow, okay, so it looks like our score is 99.99999%, which is a very high score. And what this means is that given a value for all of these numerical fields, we were able to guess what the total score will be within 99% accuracy, pretty much. So this actually should be pretty self-explanatory, and it's actually a little bit like redundant doing this model selecting all of the numbers or all the numerical columns, because if we think about how the data set works, the total score is literally just based off of the numerical score of all the other fields. So this number, so when we look at like our data set, and let's take for instance the US, we look at all these numbers basically culminate to like make our total score. So it makes sense that if we're taking in every single one of these variables, we should be able to predict our total score almost 100% correctly. And our model actually does reflect that pretty well, because obviously we have an accuracy of almost 100%. But in general, multiple linear regressions are going to be more accurate than single linear regressions or simple linear regressions. And this can obviously kind of vary case by case, but generally it holds true, because if we're factoring more than just one variable, it'll typically only make the model get more accurate, because we're just basically feeding it in more data. So if we go ahead and just run our loop again, you can see the predicted values are actually very, very close to our actual values. And when I say very close, I mean pretty much exactly. Like, right, let's look at, for instance, like this one right here, predicted 15.487, actual value is 15.48. Right here, predicted 31.3599 is 31.36. And honestly, I think this model probably does have 100% accuracy. The thing is, the reason why it's not perfectly 100 is because of the rounding. I'm guessing these scores here might be rounded for what we have in our actual columns, which is why our predicted values go a bit further in decimal place, but are actually pretty much exact if we were to round on most of these. This is technically the very last episode in the series, but we're actually learning new things. As the next episode, the definitive last one, will just be us going over everything we've learned with a brand new data set and piecing it all together. Before we wrap up with this data set though, let's write up a super quick and simple analysis of the data set we've been working on throughout this series. So as a fun little experiment, I actually plugged in basically the data set that we had and some of the information from it into ChatGPT, and here's what I got as a basically a data set summary. So it says the analysis of the data set tracking the AI global index of 62 countries revealed interesting insights into the factors contributing to a country's total score. Among the various fields evaluated, such as talent, research, and operating environment, It was observed that a country's total score displayed a strong correlation with both talent and research. A simple linear regression model achieved an accuracy of approximately 75% when using research as a predictor for the total score. However, the accuracy significantly improved to 99% when employing a multiple linear regression model that incorporated all the scored fields to predict the total score. These findings highlight the crucial role of research in determining a country's overall AI capabilities, while also emphasizing the combined influence of multiple factors in shaping its performance. And with that, we'll formally wrap up this episode. In this episode, you learned about simple and multiple linear regressions, how to train them, how to test them, and how to view the accuracy of the models in both number form and graph form. I strongly commend you if you made it this far in the course, as I know it's not easy to learn something new, especially something that can be pretty intimidating like data analytics. In the very next episode, we'll summarize everything we've gone through by walking through a brand new data set, employing everything that we've learned so far. I'll see you in the next one.